I'm so delighted to have this conversation. I had spent a wonderful long Zoom with you a few weeks ago, researching the story that I have written, or at least in draft form. But you have so many great stories to tell. I'm excited to share this conversation with other people and not just keep it to myself. I want to start a little bit with your story, your kind of biographical story, because there's some wonderful anecdotes that you shared when we talked before. Tell us about your initial encounter with programming and computing, which didn't go so well.
Right. So there's this stereotype that a true engineer always took things apart when they were little. I never took anything apart. Never occurred to me to do that. I assumed I would break it or get electrocuted or something. So, but I was always the best student at, math or science classes and stuff, and I kind of knew that was going to be the case, and I wasn't even happy about it. It's like, okay, next year we're taking chemistry. I'll be the best student. But I had a fantasy that some boy would do better than me at some math or science thing, and my plan was to fall in love with him and marry him. So the reason that I start with that background is my first introduction to computers was that a teacher in high school noticed that there was a programming class at a nearby college, and the timing worked out that she could sign a few of us up, drive us over there, wait for the class to be over, then drive us home. Teachers are just awesome because she didn't get paid for this or anything. So I walked into the class and everyone was bragging about how they had built ham radios when they were 7. I had no idea what a ham radio was. I was quite sure I wouldn't be able to operate one if I stumbled on it. And they were asking questions with fancy words like input. I had no idea what that meant. And so for the first time, I got nothing out of that class because my mind shut down and I felt like, oh, there's so many years ahead of me, I'll never catch up. Which makes me a good teacher because I understand the sense of panic that can cause someone who's perfectly capable of understanding things. So I did wind up eventually learning to program. I was actually in a physics class in college, and the TA said to me, I have a project and I need a programmer. Would you like to be my programmer? And I said, I don't know how to program. And he said, yes, I know. That's why I'm asking you. I have no money to pay you. And if you knew how to program, you'd expect to get paid. You're doing so well in the class. I'm sure you're bright enough to figure it out. And the reason I agreed, to be brutally honest, was that I had a boyfriend at the time who knew how to program, so I figured that he could. So yeah, I needed sort of a friendly environment for this thing that I had decided, I couldn't do. And yeah, so I was able to do that. Yeah.
Let's just talk about your romantic life, because it seems to be coming up. Let's just step back a second, that period. So you're at MIT, and it's late 60s, early 70s kind of time frame?
Yeah, early 70s.
Yeah. And there's something I read, we didn't talk about this, but there's something I read where the MIT, the female students, the population was capped by the number who could fit in the dorm. Is that right? What was the story with that?
Yeah, so my freshman year, it was still, they could only accept as many women as could fit into one very small dorm.
There was just a woman's dorm.
Right.
And they were maxed out if there were any more
so a
candidates.
ratio of like between, like 1 in 15 or something, which seemed kind of cool at the time when I was going there. Also, I thought it was cool because MIT did not have a phys ed requirement for girls. It did for boys.
Really?
Yeah.
That's pretty funny.
If we got into trouble, thered be some boy around to rescue us. They also had to pass a swimming test, and we didn't, whatever. Yeah. What I realized
You had all this extra time. No wonder you became such a successful...
Right. But yeah, I'm sort of extremely empathetic, and I realized, the school was full of these incredibly shy, awkward, sensitive boys, and who had never spoken to a girl before. And I'm so approachable. If I would just merely say hello to one of them, they'd get all excited. I'm going to get married now.
Yeah. I talked to an actual girl.
Right. And I felt so incredibly bad about that. Actually, there was a hardware class. There was a digital hardware class that I was taking. The thing that was most difficult was there was not enough equipment. So you had to build your project. But in order to do that, you had to go around and say to people, oh, do you have any extra AND gates? Can I use your oscilloscope? And being the only female in the class, I sort of discovered to my horror, there wasn't anything I could ask one of these students that they wouldn't say, go ahead and take it. You need the scope, go and take. Do you need a kidney? Whatever. So I got my project done really quickly, and then I decided I owed it to the world to help the other people. So I'd pick some kid and I'd say, okay, what do you need? And I'd go and gather it all for him, and he could. And once like 5 or 6 people got checked off, there was enough equipment for everybody else. So there's this famous computer science problem known as the dining philosopher's problem. But the basic idea is that if you have a bunch of processes that all need to grab a certain set of resources, if they just grab what they can and then wait for the others to get free, you'll have a deadlock. So there are all sorts of solutions to this thing. But I discovered that the solution that I discovered was introduce a woman.
That's great. Now, but by the way, I just want to mention that we will leave, a couple minutes at the end here if anybody has any questions. So please, think about that. We'll have time for maybe 2 questions. So if you do have them, store them in your brain. I don't know if I have the timeline right, but was it around this period at MIT that you worked with Seymour Copper, who is a kind of legendary figure in history of programming and education? Tell us about that.
Yeah, so this was like a whole other life that I had completely forgotten about. So I was, as a programmer, that I did learn how to program so then I could get part-time jobs and get paid. I was in the Logo lab. Logo is where I was implementing the language, doing debuggers and that kind of stuff. And it's a language for teaching kids programming. So it was kind of oversold. They basically said, it's such a powerful teaching paradigm that just put a computer in the class and the kids will teach themselves. And then they trot out the same 12-year-old son of one of the professors to show off to the press, and they'd be all impressed with it. So I decided, and it was using like an ordinary keyboard where you'd say forward space 100. And I decided to teach all of the same concepts, but without needing to use a standard keyboard. So, I built special keyboards with just buttons that you would push that would do what you would do. And sort of the ultimate one was something where you could actually program, where a command was a physical object, and you plugged the physical objects together to create a program. Now, I was embarrassed by the whole thing because I was, being the only woman around again, I wanted to be taken seriously as a scientist. And my project involved teachers bringing in these adorable little kids, and that didn't seem like science to me. So, I was happy when I sort of moved on to other things. But so I had completely forgotten about that until, like 20 years later, someone from the MIT Media Lab got in contact with me and said, are you Radia Perlman? And I was thinking, why, yes, I am, thinking that he'd, talk about network protocols. And he said, you're the mother of tangible computing. And I said, what's that? It's the idea of creating a program by physically plugging the individual commands together.
You're the mother of so many things, it's hard to keep track.
I also have 2 sort of carbon-based.
Life forms, yes, mother of multiple things. So you alluded to network protocols there. I loved hearing you talk about the way that kind of thinking worked with your brain. There was something where, once you found yourself into that world of designing protocols, it locked into something. And I think it's such a great model, whether you end up doing, network protocol design or anything else. It's just, as you're going through the world, when you find something like that your brain just seems to be in sync with, it's such a powerful experience. So talk to us a little bit about how that came about and what that was like.
So the ideal team has people with different strengths, and so that you can complement each other's strengths, rather than saying, you have to be good at making public presentations and you have to be good at stringing wires and all that. So I'm very different from other people, which is what makes me really valuable. So one of my superpowers is I have no memory whatsoever. Other people could get through school by remembering what the teacher wanted you to say on a test and just sort of parroting it back. I have to understand things like so deeply that I can figure them out from the two basic principles I can remember. If you ask me to remember a third thing, I have to forget something important like my name or something. So when I approach a problem, I have to get rid of all irrelevant details to get to the conceptual heart of it. So the very idea that I can't remember all of these things at the time I'm trying to concentrate on the problem means that I see it in a sort of very simple way. So after, I've never done anything hard, after I solve something, people will look at it and say, well, of course, any 11-year-old could have done that. Whereas, like other people approaching the same problem will just start writing code when they sort of vaguely know what they're doing and it doesn't work all the time. They add more code and they come up with this really complicated thing and everyone's all impressed. But so I have to sort of get to the conceptual heart.
It's such an interesting period, that stretch of time in the kind of middle of the early 70s, middle of the 70s, when a relatively new science of understanding networks, starts to go from being this fringe thing that a very small number of people are focused on to suddenly, oh, wait, the entire world is going to be dependent on these kinds of systems, and they have to be resilient. They have to be stable, and we don't yet know how to make them stable. Was there a sense in that period that the overall significance of what was coming, or were you just drawn intellectually to the problem of how do you make these networks more efficient and more stable?
Right, so networks at the time were really kind of a way for researchers at universities to share files or something. And it was part of the education was having these things be so complicated that you would learn a lot from it. But when you have a network in a hospital, doctors shouldn't have to be IT people. They have enough to worry about cutting people open and stuff. I wound up sort of in the right place at the right time, which was designing networks for digital, which was a commercial product for real people.
Digital, the company.
Digital Equipment Corporation.
So Digital Equipment Corporation, which was at the time one of the bigger tech companies in the country.
One of the companies I put out of business, apparently. But it was just this incredible opportunity that I didn't have to fight with standards bodies or anything like that. I got to be the person to design things. Now, I hate gadgets. I barely know how to use my smartphone, and I was designing things for people like me. I wanted it to you'd plug it together and it would work. I kind of liked the algorithm they used in the ARPANET for doing one of the things I was doing. And so I said I wanted to use that for DECnet, and my manager said, well, he was never convinced it was stable. Can I prove it was stable? And after looking at it a while, I said, oh, wow, it's not. A few bad messages, and the network would be down forever. Now, with your PC, when it gets into a bad state, you reboot it, you can't reboot a network. There's no on-off switch on the entire network. So, one of my first papers was saying that networks have to be a lot more resilient than something like a PC, especially because the way you diagnose the problems and fix things is by sending messages across the network. And if the network is broken, how do you do that? And then I also said, this particular algorithm is not stable because of this, and this is how to fix it so that it will be what I called self-stabilizing. Once you get rid of whatever node is corrupting its memory or whatever, and everyone else is doing the right thing, then it will return to normal operation. So what's kind of interesting is after that paper, the ARPANET actually did fail the way that I was predicting. But yeah, so kind of my contributions that I'm quite proud of are making networks much more self-configuring, so you don't have to worry about them terribly much. As a matter of fact, the spanning tree bridge thing, one of the people at Digital complained to me that some of the customers are unhappy because it's the most boring product that Digital ever did. You just plug it together and it just works. Yeah. And so I said, fine, if they want knobs, I'll put in knobs that they can play with, but you don't have to touch the knobs. And if you do touch the knobs, you can't hurt yourself. Any setting will still work. So that's kind of the philosophy. And then I also did things to make it be able to scale much bigger and stuff like that.
I like that idea that, before the work that you did and the work that others did, we could have, if that hadn't happened, we would have been in a situation where like the internet would fail in some way, and we would all have to, all across the world, turn our routers on and off in sync. Right. 10 billion routers, like turn on and off. Okay, everybody, let's do it. We got to restart the network. So thankfully, we don't have to do that. So you mentioned spanning tree protocol. This is the thing you're probably most famous for.
Yeah, just because it has a nice sound bite, spanning tree protocol.
Yeah, well, well, there's a lot of poetry, as we will see in this idea. So two-part question. Give us, as best as our brains can grasp it, a description of the problem that spanning tree was designed to solve.
Right. So the industry made a mistake, and instead of doing sort of networks where data is forwarded from link to link to link, the Ethernet arrived with great fanfare, and Ethernet is a way of getting a couple hundred nodes on a single wire. It doesn't scale beyond like a building or a few hundred nodes. But then people started building their applications that talk directly on Ethernet without this extra layer that was designed to move from link to link to link. So I tried to argue with them and saying, no, you still need my layer, which is layer 3. And they said, oh, Radia, you're just upset because no one needs your stuff anymore. And I said, well, they may want to talk from one link to another. And they said, our customers would never want to do that. So they built their stuff, and they made a lot of money for the company because it was good stuff, but it would have been just as good had they done it correctly, which is on top of this layer that lets you forward. So years later, I'm sort of in a bad mood, and my manager said, we need to design a magic box that will sit between two Ethernets and let someone over here talk to someone over there, which is what my stuff did. But my stuff required the end nodes to put it in kind of the right envelope and stuff. So this was, they wanted to invent some sort of kludge that without the end nodes knowing that their stuff would be forwarded, that they would think they're speaking on a single Ethernet, and yet it would move around. So it's simple. You just, these bridges, these magic boxes, listen promiscuously, store the packet up, and then when the ether is free, they forward it onto other ports, which only works if there's no loops. If there's any loops, it's not going to work. So he challenged me to write, to design. He said, you do this distributed algorithm stuff. Figure out something that with 0 configuration, you just plug it together and these bridges find a loop-free subset. And he thought it was going to be hard. He asked me on a Friday, and he was going to be on vacation the following week. And this was before there was email or cell phones or anything, so he was going to be unreachable. And he said, just to make it more challenging, make it scale as a constant. So no matter how many bridges and links there are in the world, the amount of memory necessary to run this would be a constant, which is crazy. Nothing's a constant. You know, the best you can do is sort of linear. Maybe it'll wind up being the square of the number of links or something. So that night I realized, oh my goodness, it's trivial. And furthermore, it scales as a constant.
Just you went home and the vision of it came right into your head.
Yeah, you just kind of think about it the right way. So, yeah.
Did it come into your heads this week?
So I knew just how to do it. I could prove it worked. Monday and Tuesday, I wrote the specification in enough detail that when the implementers were implementing it, it only took them like a month or two, and they didn't even have to ask me a single question. So the spec was all complete, and this is the end of the day on Tuesday. And what was I going to do? Because I had to show off to my manager, and he wasn't around. So I spent the remainder of the week working on the poem that goes along with the algorithm and was the abstract of the paper that I published the algorithm in. So I officially spent more time writing the poem than I did inventing the algorithm and writing the spec.
You did not realize you were coming to a poetry reading tonight.
Right.
Can you recite the poem?
Yep. So the poem is called Algorhyme, because every algorithm should have an algorhyme. So I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the route must be selected. By ID, it is elected. Least cost paths from route are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree.
I think there is very little precedent for this in the history of software. That almost all the innovations, that's what, as I'm interviewing people for this series, I'm going to be like, well, no, that's impressive, but what's your poem? Do you have a poem? And last question on Spanning Tree, was your boss impressed?
Oh, yes. Except, well, to be totally honest, just to sort of give you insight into the world, I'm also passionate about corporate culture. And the culture was sort of dominated by these very aggressive, pompous people that everyone assumed were geniuses. And to give you an example of if you asked a question, especially in public, one of these people would say, if you don't know that already, you don't belong in this group. Now, they never actually did anything worthwhile, but my manager thought of them as geniuses, and I just made him nervous. He couldn't quite figure out what to make of me, but he was really brilliant and would understand the import of something that I did. So several times, I would leave the spec on his desk and he would read the whole thing and he would be amazed, but then he'd say, how did you think of that? Which was kind of annoying. He never really, he meant well, but just, not all of us in this industry particularly have great social skills.
Right. I hope he eventually saw that you got into the Inventors Hall of Fame. And
yeah, actually, he asks me questions sometimes. I give him work as sort of an expert witness at patent trials because I get offered that, but my company always says no. So I suggest him. And so sometimes he asks advice. And one time I said, I explained something and I said, this is something that you were, this person that you were always so impressed with, that was why his stuff wouldn't work. And so for the first time, it took him like several days to get back to me. And then he said, well, if by impressed you mean bamboozled, I plead guilty, but I'm not asking him for any technical advice these days. So yeah, it's sort of all worked out.
I did just want to mention that, one of the other extremely valuable contributions you made to the field of network design, protocol design, is a really classic textbook, Interconnections.
Yep.
That it's multiple editions. And I think you can see tonight, that you're just a wonderful explainer of ideas, and that I think, made a massive impact on a whole series of generations of people who went into this field. And I was really struck by this quote from I think it's an introduction you wrote to the second edition, about the field of network design, but I think this applies to a lot of things in the technology world. You said, there's considerable confusion in this area. Most of the terminology is ill-defined and is used in conflicting ways. The terminology and the specifications tend to be daunting. Some knowledge is spread among many different documents. Much is unwritten folk wisdom. Adding to the confusion is dogma. Beliefs are accepted as truth, and questioning of any of the dogma is often greeted with hostility. But good engineering demands that we understand what we're doing and why, keep an open mind, and learn from experience, which is just very wise advice. And I guess my question is, there are folks here who, I think are hopefully, part of what we're trying to do with this series is inspire people, inspire the next generation of hidden heroes and innovators. And, of all the advice and the wisdom you've kind of accumulated over all these adventures, what's some of the pearls of that wisdom that you could share with folks?
Yeah. Well, by the way, the book is the reason why I just happened to write the book. I do like explaining things, but it was why I became known. Because before that, I'm not somebody to, thump my chest and say, me, or act like, someone that seems important. But as a result of the book, which became the book everyone had in their office, when somebody would be introduced to me, they'd sort of take one look and it's like, yeah, but then they'd hear the name. It's like, oh, like the book. Yeah. So that really changed my life. But in terms of pearls of wisdom, how to actually design things. In that book, actually, I have these little boxes where I try to, I say real-world examples, where I try to explain something with a real-world example. So scalability, I'll talk about the wine glass clicking protocol, where everyone has to click everybody else's glass, which works okay with maybe 4 people, but when you have 10 people, it's really getting awkward. But the one that's absolutely everybody's favorite, and it's 100% true, and it's to illustrate this problem in the industry that you should know what problem you're solving before you try to solve it, which seems obvious, but people don't do that. They instead say, oh, here's this shiny buzzword, blockchain. How do I use blockchain? How can I incorporate blockchain into this other thing, rather than just, wait a minute, what problem are you solving? So anyway, the anecdote, which will forever cement in your mind why you should figure out what problem you're solving first, is that when my son was 3, he ran up to me crying, holding his hand up, saying, my hand, my hand. So I took it and I kissed it a few times. What's the matter, honey? Did you hurt it? And he said, no, I got pee on it.
That's the kind of wisdom that this series is going to try to impart. So I think that's a perfect place to open it up to see if there are any other questions, P-related or not, whichever. Yes, right there.
If you were, I don't know, in college or a young professional today, thinking about where you would want to chart your career, what do you think would draw your attention?
Well, that's kind of interesting. I made no plans. I just sort of knew, get good grades, get into college, major in a hard major. So I started with physics until I got to quantum, and it's like, I'm out of there. And so I went to math. You know, there's the standard thing. You start in physics, and then you go to math, and then you go to computer science, and then you go to humanities or something. But so I wound up, you know, sticking at the math level. But I had no idea what I was going to do. If you'd asked me when I was young what I was interested in, I certainly wouldn't have said, oh, I want to design network protocols. I would have said, well, you know, I'm kind of interested in anything. And then once I took the computer class, I would have told you, oh, I'm interested in anything as long as it doesn't involve computers. But yeah, it was just a sequence of total random events that led me to where I am. So I'm not sure that I would tell people, you know, you should go into cloud native or zero trust or, you know, some sort of shiny buzzword. I would just say, you know, learn about a lot of things, learn to think cleanly. And, you know, as a math major, I dropped out, but then I went back 10 years later to get my PhD in computer science. I figured I should take computer science classes. And they kind of drove me crazy because math was crisp and clean. You could fly in from Mars, take a math class, and ask the professor what's a number and get a clear answer. Whereas here I was taking computer science classes, and the professor was waxing rhapsodic about object-oriented programming or something. And so I said, well, what is that? And it was like, everybody knows. Well, I don't. You know? And so then once I sort of understood it, it was like, wait a minute, you're just saying we should have a library of routines with well-defined inputs and outputs? I knew that. You know, what's this? Yeah, so being able to think cleanly, not to just accept things that you hear as truth, you know, you'll be able to do well at sort of any field, I guess, might be my advice.
Yeah, one more question. Did you have right there? Yeah.
What do you make of technology today? I mean, networks, blockchain, I mean, do you try to follow that? Or, I mean, it's overwhelming for us, but how do you feel about everything that's happening with technology today?
Yes, well, I love to explain things. So like when everyone's confused about what is blockchain, you know, I then sort of sort it out and explain what it is and what it isn't. Yeah, it is hard to learn things because, you know, like not everything on the internet is true.
What?
So if you try to read things by looking at the hype, the marketing hype about things on the internet, you'll think, I didn't quite understand this. Maybe if I listened harder or something, but a lot of people are just sort of spouting nonsense, you know, grammatically correct sentences where you know all of the words in the sentence and still it doesn't mean anything. Yeah, the internet, I used to be so excited about how it has changed society. You know, any merchant can reach a worldwide audience, and if you need a weird widget from, you know, and the only merchant is in some country you never heard of, somehow you can send money and somehow the widget appears. This is all magical. And all of the knowledge you need is available for free. But so is a bunch of incorrect things. And I understand like all of the cryptography and protocols involved in the security on the internet. And then there was this thing that happened that made me realize there is zero security. So I was wanting to renew my license, my driver's license. So of course I did a Google search. renew Washington State driver's license. And I clicked on the first thing. Had I bothered looking at the URL, the name inside, the DNS name, was perfectly reasonable. It was something like washingtonlicensing.org. So I clicked on it, went to a website that had all these pictures of very happy people holding up licenses. And you could click on renew your license, get a new license, replace a stolen license or whatever. And it asked me what I expected, which was my address, my license number, and my credit card number. And mission accomplished. Now, I wouldn't have noticed anything wrong except, 8 weeks later, my license wouldn't have appeared. But the bank fraud department called me and said, are these charges legitimate? Where every day, these places, the scam artists that I had actually gone to, charged more and more. So it was $3.99 the first day, $9.99 the second, $19.99. And at that point, the bank called me and I explained the problem and they disallowed the charges and gave me a new credit card. So I was not injured at all, and it gives me a great example that all of this cryptography in the world is not actually helping us because, and I also claim I did nothing wrong. I like to be an advocate for humans. So when people go around saying, well, we need more user training, or users shouldn't click on suspicious links, it's like, what's a link? What's a suspicious link? So a challenge to the other people is make things that are, understand that a human is part of the equation, and don't put the burden on them. Design things that will work the way that humans, there's actually a quote, if I can, from my security book that I wrote it, and I've actually seen it on quote boards. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It is astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our protocols around their limitations.
Well, that, I think, makes us feel bad about ourselves as a species, but is probably a great place to end. I think you've probably seen tonight why, when we were coming up with a list of who should the heroes be, that Radia Perlman was right at the very top of that. What a hero. Thank you for joining us. It's been really special.
Thank you.